So we're picking up on 17. As a reminder, this is a velocity time graph. Okay, so that's the key, is that this graph here is velocity, as opposed to it being a distance graph where the slope is velocity. Okay, 17 is asking, what is the average velocity of the particle over the 5-second time interval? Thoughts of how we would find average velocity?
I don't know if you can like add the four slopes together and divide it by 4. I know it's acceleration to be 6.
If we're, let's see, I'm trying to think how I want to explain this. I'm trying to look for a problem to reference from yesterday, and there we go. So back on 11, we talked about average velocity over the, so on 11 we talked about average velocity over the time interval from 2 to 3. I know, Logan, you and I had differing ways here, but I looked at it as a change in distance over the change in time. Well, in order to find distance on this graph, it's not a distance graph, it's a velocity graph, it's the area under the curve. Okay, so distance is going to be the area under the curve there.
We already know the change of distance.
Well, okay, and so what?
7.5 feet to the left, or -7.
Okay, so the idea, and I was going to write it out, we had already talked that the area under this piece is 7.5, right? Okay, just doing the basic area, that represents an area of 7.5. The area down over here in that triangle is 15, but because it's below the x-axis, it represents an area of -15. And so what I basically did, again, if we're doing change in time over change in distance, 7.5 minus 15 over our 5-second time interval means divide by 5. And so -7.5 divided by 15 is going to be,
Divided by 5.
excuse me, divided by 5 is going to be -1.5. And what are we in? Is it feet per second?
Yep.
Yeah.
Not units.
What?
Not units.
I know. I don't have a lot of units on mine, honestly, so. Okay, so change in distance over change in time. Because it's a velocity graph, distance is the area under the curve. Now, the question, next question, I'm not sure why they're just now asking this. Are the answers to 15 and 16 the same, and explain?
No.
I think we kind of talked about this yesterday, and this is where I really wish I had the notes from yesterday. I don't even have that screen up here. This makes it difficult. So 15 asked us total distance, and the total distance traveled was 22.5.
Are 15 and 16 the same? No, because one's 22.5 and one's 7.5.
Okay, but I'm trying to get the explanation, and I'm trying to help Eli out here a little bit. To not thoroughly confuse them, kind of leave them in the middle maybe somewhere. Who knows? Okay, but total distance. And that is, if I walk back and forth, that's adding up all the distances. Okay, so that was 22.5. Particle's position after 5 seconds, well, if I go forward some, backwards, forwards, backwards, it's just, it doesn't matter how many times I go forwards and backwards, it's the distance from point A to point B. Okay?
So start to end.
Right. So start to end, ignore all the overlapping pieces. And that's what we call displacement. Okay, so the answer on 18, no, they're not the same, as Logan's going to clearly point out. It's total distance traveled, which is adding up all the times, which that was number 15, versus displacement.
I feel like that was like 7th grade science.
It very possibly is. I'm just not assuming you remember your 7th grade science. I'm not going to say you didn't already know that, but I would assume you need the reminder. Okay, what is the average speed over this 5-second interval? Well, how do we find speed?
Just the absolute value of velocity.
Okay, how are we going to find velocity here?
We already have that velocity.
Then I don't think I can agree. I can't agree with that.
How is it not just
So average speed is going to have to be used
22.5 or
all the distance traveled. If we're talking average speed, we have to use all the distance traveled divided by that time. And the whole distance traveled was the 22.5 divided over that 5-second interval. Okay? And so that works out to be 4.5 feet per second. What is the particle's acceleration over the first second, and what does your answer mean?
0.
And
The slope of the line is 0.
yeah, so if this is a velocity graph, then remember acceleration is the derivative of velocity, and that derivative definitely is 0. So what is the particle's acceleration? That's going to be 0. Label, if you want it, would be meters per second squared.
Feet per second squared.
Gosh darn it.
That's it.
What does this mean?
That the velocity is not increasing in the first second.
Okay. I use the word constant. Velocity is constant is what mine says, but yep. It's not increasing or decreasing. Velocity is constant. Over what time intervals does the particle have positive acceleration?
Between 3 and 5.
Yeah.
Yep, you got it, because my slope is increasing there. 3 less than t less than 5. And my comment here is that velocity increases. Over what interval does it have negative acceleration?
1 to 3.
1 to 3? Because that's when the velocity is decreasing. When is the acceleration undefined on the interval from 0 to 5? So when is acceleration undefined?
T equals 3.
That's one answer.
I was going to say each sharp point. So
Yeah, so
P equals
Okay.
1, 2.
Yeah, so technically it's 1, 2, and 3. I mean, 2 doesn't look much like a sharp point, but it doesn't come together in a smooth point, so we count it as a sharp point. So when the derivative, DNE, or sharp cusp, and so 1, 2, t equals 1, 2, and 3. When the derivative does not exist, which is sharp points or cusp. Okay. 24. State an interval of time when the particle has positive acceleration but is slowing down. Positive acceleration but is slowing down.
There is. I was just waiting to see if you.
Give him a chance to think
Yeah.
before you. I appreciate that because
Yeah. Slow down. Positive is
I said between 3 and 5. Because
I know it's positive, but
so the acceleration is positive,
Mhm.
and so since the negative velocity is going to decrease, the speed is going to decrease. If that makes sense. Because speed is like the absolute value of velocity.
okay, so because
So like
the slope at 2 and between 2 and 3 was 10, and between 3 and 5 the slope is what would that be 5? Is that the slope?
well, it's just
it's
so
the fact that it's a positive slope.
Yeah.
at t equals 3, the velocity is negative 10, right?
Mhm.
So speed is the absolute value of velocity. Like it can never be negative. And then at 5, the velocity is back up to 0. So that whole time, the velocity is getting closer to 0, which means the speed is decreasing. So it's technically slowing down.
Okay.
Back on page 144, when you go through the notes, there's a chart we talked about, and the idea is in terms of speed. Anytime your acceleration, your velocity have the same sign, so both positives or both negatives, then your object's going to be speeding up.
Gotcha.
You're going to be slowing down anytime you have opposite signs. So positive acceleration with negative velocity or vice versa.
So because it's negative and increasing.
Right. So we got an increasing acceleration, but we're on the negative half of the graph, so we have a negative slope or a
Gotcha.
negative velocity. Okay. So what was that, 3 to 5? And
So would that mean that 25 is from 2 to 3?
I agree with that.
And I agree with that, yeah, because you want acceleration is negative, but particle is speeding up. So when we see speeding up, you're thinking same sign.
Yep.
Is that making sense? See, some of this will make sense when you go back through the other notes. Okay. What is the particle's acceleration over the time interval 3 to 4? What do we know about acceleration? Acceleration is the derivative of velocity. So it's the slope. What is the slope from here? So we're going to, what'd you say?
5.
5. Yep.
Okay.
Yep. So acceleration is the derivative of velocity, which is slope, and it is 5. Technically, it would be 5 feet per second squared. Okay. What is the particle's average acceleration over the entire 5-second time interval?
You add up the 4 slopes and divide it by 4. And then
No. Think in terms of average acceleration, kind of like a rock. And so we're going to be looking at velocity minus velocity over time minus time, if that makes sense. And so if you look at the velocity at 5 minus the velocity at 0 over 5 minus 0. Okay. So when they say average acceleration, velocity at 5 minus the velocity at 0 over 5 minus 0. The velocity at 5 is 0. That's just a point on the graph. Minus the velocity at 0 was 5. You end up with
meters per second squared, feet per second squared.
Yeah, you kept correcting me earlier. Okay. And last one of this forever long problem. Over what time interval is the particle's velocity decreasing at a rate of 5 feet per second every second? Now, 5 feet per second every second, realize that's a long way of saying 5 feet per second squared. Okay, that's a big hint right there of what we're looking for.
It's just from 1 to 2.
1 and 2.
Yep.
You said this physics stuff was hard.
Oh, this is the beginning stuff.
I will say, we don't go
The
horribly
only
deep
reason I'm
into
good
it,
at
but
this stuff is because this is stuff you have to do for everything else.
Yeah.
so this is the stuff that by this time last year they had already learned.
Until you start talking about fluid flow rates and all that crap.
Okay,
Dynamics.
so Eli, you can have fun doing the first 16 parts of that one. So, okay,
This is only 2 questions long.
No. Example 5 had 28 parts, and they label it that way. Okay, example 6, let's fill in this chart. Complete the table below to find all possibility for an object's motion. Remember that an object's velocity is either positive, so moving right or up, or negative, moving left or down, or 0, meaning it stopped. An object's acceleration is either positive, negative, or 0, as in constant. Okay, so when velocity is greater than 0 and acceleration is greater than 0, what is my particle doing?
Increasing to the right or left. Being pushed
So-
right or up.
Huh?
Being pushed right or up.
So if we're talking in terms of, we keep referring to this, what's your car doing, I guess, let me put it that way.
Accelerating.
And so it is,
Accelerating.
speeding up. That was a really long way for me to get you there.
At some speeds, they're hard.
Well, okay. No, the idea, and this is going back to the same sign stuff. Okay, at least parts of it are.
Yeah.
When velocity and acceleration are both positive, speeding up. What about when velocity is greater than 0 but acceleration is less than 0? Slowing down. What about when velocity is greater than 0 but acceleration is 0?
Cruising.
Cruising.
Cruising. Okay. Yes. So constant. What do I have here? I have constant is in the acceleration is constantly. Velocity is moving to the right. Yes. So. Okay. When velocity is less than 0 and acceleration is greater than 0, opposite signs. When velocity is less than 0 and acceleration is less than 0, speeding up because they are same signs. Velocity is less than 0, but acceleration is constant.
Speed to the left.
Mm-hmm. Okay. And, okay, acceleration is positive or greater than 0, but velocity is 0.
Speed up.
Huh?
Speeding up.
No?
Constant velocity to the right.
So our acceleration is going to push right or up. But because you have a velocity of 0, your particle has to be stopped.
Well, I was thinking, earlier how like the velocity hit 0 for a second, but then it continued into the negative area.
Well, that would be because it would, so that would be, let's see, try and think, how do I compare this? I mean, the key is the velocity, so the velocity being 0 at that point was the turnaround point, is what that was. In this case, so it stopped for a moment to turn around, and then it continued again, or moved the other way. Whereas this one, the velocity is 0 the whole time, so it has to be stopped. You can't be moving if you don't have velocity other than 0. So stopped. The acceleration pushes right or up, depending on the scenario. So what about when velocity equals 0 but acceleration is less than 0? Again, our object is stopped. This time acceleration pushes left or down. And what about when they're both 0? It is just stopped. There is no acceleration. There is no velocity. Okay, that was the big page. We do have 2 more pages to go. Can't guarantee we'll get through them, but at least they're not as big as the other one. Okay. We have a really helpful chart at the top of the next page. Has some terminology. Okay, so we mentioned displacement already. That's a good word to know. It's the total change in position. Okay, so how far from point A to B, no matter how many times you retract your steps. Average velocity, displacement over elapsed time. So again, distance from point A to point B over the change in time. Also, you can think of it as like AROC, slope of the secant line. Velocity at a time, it's the derivative of the position function, slope of that tangent line. Speed, we talked about this one the other day, is the absolute value of velocity. Speed does not have direction or sign. It's just speed. Distance traveled, the sum of the absolute values of the distances between turning points. So that is distance traveled, adding up all those steps. And direction changes. When velocity changes from either positive to negative or negative to positive at a point, velocity does not need to pass through 0 or even be defined at a point where its sign changes in order for direction to change. Okay? So, some good chart information to reference that can help you along. Okay. Let's look at a model rocket. Model rocket is launched vertically upward from ground level with an initial velocity of 114 feet per second. The position of the rocket can be modeled by this function. So position of the rocket is s of t. Notice the initial velocity of 114 is already in there. Okay, so we don't have to put that in there or anything. A asks us to find the velocity and speed of the rocket at 5 seconds. And it does say to use a calculator. But really, I think we're just using it for calculations, it looks like. So, what do we have to do?
Well, S of t is distance. So you need to get. We need to get what, that 114t equals the rest of the equation?
No. You're overthinking it.
Plug in 5 for t.
That would give me the position, not velocity. I don't have a velocity formula yet. That's what we're getting ready to create. What's the relationship between velocity and position?
Is it just 114t?
No. What's the relationship between velocity and position? Velocity is the what of position when we talk calculus terms. Velocity is the derivative of position. So if they give you a position formula and ask you to find velocity, you start by finding the derivative.
Negative 32t
So negative 32t plus 114. Now, if they want the velocity at 5, then that is just plugging velocity in, plugging 5 in. So negative 32 times 5 plus 114. And we end up with what?
46.
Okay.
Feet per second.
Negative 46 feet per second. That is my velocity. It also asked me to find speed. What about speed?
Just be 46 feet per second.
Because speed is the absolute value of velocity. So it's going to be the absolute value of negative 46, which is positive 46 feet per second. Okay? Is the rocket speeding up or slowing down at time 5?
Well, you have to find the acceleration, right?
Correct. Because this is, you're looking at, are the signs the same or are the signs different?
And acceleration would just be negative 32.
Because acceleration is the derivative of velocity. Or, if you prefer, it's the second derivative of position.
So it'd be speeding up because both the velocity and acceleration are negative.
Did you start to say something, Eli?
Yeah, that saying the second derivative of s makes more sense.
Okay, yeah. And I don't really care which way you want to think about it, but you start with position. First derivative is velocity. Then we take the derivative of velocity, or the second derivative, that's your acceleration. So in this case, it does say explain how you know. So I'm going to use a good calc explanation and say rocket speeds up since the velocity of 5 is less than 0 and the acceleration at 5 is less than 0.
I just said
Same
the
sign.
acceleration negatives.
A fancy explanation for negative is less than 0. What is the maximum height the rocket will rise?
Well, they have to find. We can't just plug 5 into the distance, can we?
No, because 5 is just the number they keep telling us. That's not necessarily the max height. That's just the number they used. What's going to be true of the max height? What's going to be true of the velocity at the max height?
0.
Yeah. So a max height, you know, that's your object going up. So we're looking for when does
14.
velocity equal 0. I don't know. What's my velocity formula?
32t plus 114.
Set it equal to 0.
Is that equal to 0?
Yeah. We're not plugging in 0 because that'll just give you the velocity at time 0. We want to know when is the velocity 0. Not what is the velocity at time 0, when is the velocity 0. So basically, when is the derivative 0? So whatever 114 divided by 32 is?
I would guess like 3 or 4.
3.5625 according to my notes. Okay. Now, that doesn't answer my question.
You put that in the Euclid equation.
Right. So that answers the question of when is the maximum height? The maximum height happens at 3.5625. So now you're going to go back to the position function and plug in the 5625, which I'm not even going to write out. This is a calculator active problem. I can just write S of 3.5625 is, and my calculator can tell me. (203.0625 feet). Oh, you guys do actually have calculators. I haven't been using them, so. Did we get it? What is the speed of the rocket when it hits the ground?
0. Or so when it hits.
Like, what is the speed on impact? Not the ground forces it to become 0.
So you would double the time of 3.5625 and then plug that into the velocity equation, and then find the absolute value of that.
That would very possibly work. It's not how I did it. And I think, yeah, it would end up working. I looked at what do we know when the rocket hits the ground? Besides the fact the velocity is going to go to 0 here momentarily, what's the height of the rocket? 0. So I looked at, officially you're looking at it as setting the position equal to 0. Okay. Now, with that in mind, so negative 16t squared plus 114t equals 0. And I'm not disagreeing with the doubling. Okay, this is just my official term, what I should. Yeah, well, okay, so good news is there's usually a GCF. Oh, actually there's not here. I was going to say there's usually a GCF of 16 in these, but there's not. We need GCF. They're both even.
See, this right, I think it's much easier to have factors of 114.
Okay, well, just try factors of 16. 2 goes into it. Does 4 go into it? If 4 doesn't go into it, stop there. It's going to have to be 2. Because if 4 doesn't go into it, 8 can't go into it, and 16 can't go into it. So, if you factor out negative 2t, I'm left with 8t minus, what was it, 57? If you set each factor to 0, what do we have? Negative 2t equals 0 would give you t equals 0. 8t minus 57 equals 0 gives you t equals 57/8. There's 2 times there because one is when the rocket starts and the other is where the rocket ends. So obviously we're going to use this time. What's the speed of the rocket? How do I find speed? Absolute value of the velocity of 57/8. Which works out to be a familiar number.
Negative 114.
Except we're doing the absolute value, so positive 114. Okay. Okay. These can be very easy problems. You just have to keep straight what they're asking and,
I honestly probably would have preferred the other way on that.
Yeah, that's not a way that I've ever been told to teach it. And
Because it's going to take the same time to go up.
I get it.
Be good now.
I get it. I mean, back to the whole parabola thing. So,
Unless gravity's stronger on the main head.
But it's not going to. So.
Okay.
Unless it's
thrust is
changing.
more.
Unless it's changing planets in that parabola. But it's not.
unless the parabola goes out of the Earth's atmosphere and into the moon atmosphere type thing. Yeah. Okay. We know that for very small values of h, the approximation of the derivative can be found by the difference quotient. And that's that f of x plus h minus f of x type stuff we've been doing. It can be shown that the approximation can be found when h equals 1. That is, That's what I just kind of mentioned. Now, to clarify, f prime of x is approximately equal to the change in f caused by a 1 unit change in x when x is equal to x naught, as in your initial x value there. Okay, so they're just saying two values very close to each other, you can find an approximate change there.
Why does
Okay,
it say 0 plus 1? Why didn't it just say 1?
Because if it's x plus h, the h value is the 1 there, because they had h as 1.
We should just put h instead of.
Okay, now let's look at example 8. For speeds between s equals 30 miles per hour and s equals 75 miles per hour, the stopping distance after the brakes are applied for a vehicle can be modeled by the formula f of s. For a vehicle traveling at 65 miles per hour, find the actual stopping distance at 65 miles per hour and 66 miles per hour, and what is the stopping distance needed for an increase in a speed of 1 mile per hour. So, find the actual stopping distance at 65 and 66. What are we going to do?
Again. 65 and 66
Yeah.
for s.
The formula, f of s, is the stopping distance after the brakes are applied. So, first thing you're going to do is you're going to find f of 65 and f of 66. Now, I could write out that it's 1.1 times 65 plus 0.05 times 65 squared. But in all reality, what are you going to do? You're going to plug that into the calculator, right?
So what is it? Oh, we're trying to.
Or we've, okay, yep. Okay, so f of 65 is 282.75, and that would be feet. F of 66 is 290.4 feet. So what is the stopping distance needed for an increase in speed by 1 mile per hour? What are we going to do? Subtract them. F of 66 minus f of 65 is 7.65 feet. Okay? Now, it asks us to estimate the change in stopping distance if speed is increased by 1 mile per hour by using the instantaneous rate of change at 65. What do I mean by instantaneous rate of change? We need the IROC, the derivative. Okay, so first of all, if we do the derivative, f prime, that's going to become 1.1 plus
Pardon an interruption for a few after-school announcements.
0.1s.
Football and Powder Puff will be tonight at 6 p.m. Volleyball will start around 8 p.m. Coming out to support your grade level. Happy 18th birthday today to Logan Sargent. Thank you for being in the hallway. Wishing a happy birthday. Also, soccer will play at Wabash tomorrow at 2 p.m. Good luck, boys, and everybody have a great weekend.
Who does that, Karen?
That's Jen.
I was going to say it did sound like Jen.
Yeah,
But
Jen's here subbing for Christy today.
I didn't know that.
Someone told her to put
What
on
is
there.
it, 7.6?
I have 7.6 written down. I'm assuming it was exact.
Yeah. Feet per mile. What?
I know. That's what I've written. I'm trying to figure out if that's right or not.
Oh, so it's basically saying
Oh, because
a
it's
change in stopping distance.
because it was if speed is increased by 1 mile per hour, it's that many feet per that one increase of mile
So
per
what
hour.
is this saying? This is just a different estimation than we already got.
Yes. Now, C, then compare this estimate with the actual increase in stopping distance.
It's just 0.03.
Yeah. And so, with that in mind, we're looking at the 7.65 as opposed to 7.6. When you increase your speed to 66 miles per hour, your stopping distance increases by, and I have listed about 8 feet. Okay, so your stopping distance increases a little bit. when you increase speed to 66, stopping distance increases by about 8.
I don't think that's what he's asking. Yeah, it's asking you to compare the estimate and the actual.
So
Okay.
It's 0.05.
So 0.05, right? Okay. Okay, guys.